video inspiration video.
How do I change the slides? Do I just ask for the next slide or? Yes, I ask.
¿Cómo cambia? Now, try now. Oh, yeah. If you need prefer this is an old-fashioned one.
Yeah, nothing wrong with a good pointer stick.
So, bueno, muchas gracias por venir al colegio de hoy. Estamos presentando a la doctora Pattle, que vino de visita una semana acá a la Argentina a trabajar con Manuel Fernández. Ella viene de Londres, del University College de London, y bueno, nos va a hablar de los campos magnéticos en el material interestelar. I will present you now in English. Thank you everybody to came and listen the talk of Dr. Pattle. It's come from University College in London, and she's visiting Argentina for a week, working with Manuel Fernández here at the YAR and also in the La Plata Observatory. So, Kate, yours.
Thank you very much. And thank you very much for having me here. It's my second visit to Argentina, but my first to the IAR, so I'm very, very excited to be here. So I'm going to be talking today about, as you might guess from the title, magnetic fields and the role that they play in the star formation process. Mostly I'm going to be talking about the star formation process as we observe it in our own galaxy, but towards the end of the talk I will veer wildly off into other galaxies, and I don't really work in other galaxies myself, so you'll watch me get vaguer as the talk goes on. My research is really all about how you take molecular clouds and convert at least some fraction of their mass into new stars. And as a star formation astronomer, I know that the process is beautiful and detailed and interesting purely for its own sake, but I know that for most astronomers, the star formation process looks something like this. You get some gas, you put it into a black box marked star formation. With some efficiency, you get some stars out. Maybe, if you're feeling really sophisticated, you make your efficiency a function of metallicity. But for most people, this is what star formation looks like. And I don't think this is necessarily a bad thing. For those who aren't working in star formation, the interesting thing is not necessarily how the process works, but what you get out at the end. Because star formation, it's central to all of baryonic matter. Everything we understand about how galaxies evolve, how the universe evolves, depends on how we convert the interstellar medium into stars and back again. So if we don't understand star formation, then we don't understand many other things. We don't understand where the initial mass function comes from, and we don't understand whether it changes with environment. We don't understand star formation efficiency, and we don't know how it's set. And if we can't answer those questions, and we can't answer how they depend on star-forming environment, then there's huge swaths of the rest of astronomy that need to know these things. I'm absolutely not going to answer either of these questions in this talk, but I think these are the things that we should be striving for when we're investigating star formation. But I think the question, as it looks to someone who does work on star formation, is why is it just so difficult to form stars? Like, it feels sometimes like the entire physics of galaxies is fighting against star formation. You have to take low-density, turbulent, magnetized gas and get it to collapse under gravity to the point that nuclear fusion starts. You've got to overcome thermal pressure, you've got to overcome non-thermal support, which we observers lazily call turbulence, and then the theoreticians who actually understand turbulence chase us until we say we're sorry. Magnetic fields, and the effect of feedback, because as soon as you star formation doesn't happen in isolation. as soon as you turn on star formation, you start turning on the feedback, pumping energy and momentum back into your cloud. And of course, that has consequences for what happens next. These effects aren't separable in any way. I've written them down as if they're all independent, but of course they all act on one another. For my purposes, I'm going to approach them from the angle of the role of magnetic fields, but that if you want to understand any of these factors, you need to consider all of the others as well. So I thought I'd also just put up my favourite quote. I love this. It was said by Ludwig Volcher in 1967, and what he said was, "The argument in the past has been a process of elimination. You observe a phenomena, you explain the part that you can explain, and the unexplained part is taken to show the effect of the magnetic field. It therefore follows that the larger one's ignorance, the stronger the magnetic field." He said this in 1967. It's now 2024. I think we've moved on a little bit since then, but you can judge for yourselves how much we really have done. So a lot of the work, have I skipped a slide? No, I haven't, sorry. A lot of the work that I'm going to present in this talk is from the JCMT Bistro survey, which is a large programme on the James Clerk Maxwell Telescope that I'm one of the leads of. We've been mapping galactic star-forming regions in polarised light since 2017 now, so we've been going for a while, and we've amassed quite a large archive that I'm barely going to touch the surface of, but there's a lot of data out there, and if you are interested in magnetic fields and star-forming regions, we may very well have observed your favourite one. I'm also presenting things from a whole bunch of other papers, so I thank my many collaborators, particularly Xu Ping Lai at the National Tsinghua University, Jie Huang at Kazi, and Walter Gear in Galway, as well as my student and postdoc, who I will mention as we go along. So these are all of the Bistro survey papers. Like I said, I'm not really going to talk about most of them, and I know there isn't time to see them now, but if there is a region you like, please ask, and we'll tell you if we've got the data. So with that in mind, I thought it's probably worth starting with just a recap of what we think we know about star formation at the moment. And I'll start with the low mass star formation process because that's the one that we understand, at least to a certain extent. Manuel and I have been sat down this morning desperately trying to pick apart one part of one high mass star forming region. So we'll start where it's sort of comprehensible. And you start with a cloud of molecular gas. So these molecular clouds, as far as I'm concerned, they just spring into being out of nowhere. There's an entirely different field of study of how you get from cold neutral medium through to molecular gas, but it can be done. And what we find is pretty much universally within molecular clouds, where we have a cloud, we have filamentary substructure. And this filamentary structure forms regardless of whether the cloud is actively star forming or not. You see it in high latitude cirrus, like in Polaris. You see filaments in the most massive molecular clouds. It seems like they're a necessary but not sufficient step on the way to forming stars. But where you have these filaments, you see them fragmenting along their length, where they're gravitationally unstable, into a series of dense cores, sort of like beads on a string. And where those cores are massive enough, this is an example of what it looks like. So this is the very nearby Taurus molecular cloud, and you can see here the green and the blue here are some Herschel wave bands, and the red is JCMT 850 microns. And you can really see you've got these pockets of cold, dense gas, those individual cores that the filament is fragmented into. And if those cores are sufficiently massive to be gravitationally unstable, we call them prestellar cores. And a prestellar core is sort of the minimum unit of star formation. It's a gravitationally bound mass of gas that we think is going to go on to form either a single star or a single stellar system. So understanding their properties, their distribution of their masses, probably tells us something important about, for example, where the initial mass function comes from. once those cores collapse sufficiently under gravity that they form a central hydrostatic object, at that point you can genuinely say that you've formed a star. And there you've got a central object, you've got an accretion disk that over the course of time will become a protoplanetary disk, form a planetary system. You've got an envelope of material that's still falling in. And importantly, you've got outflows, because as soon as you form a star, essentially you turn on outflows that are passing energy and momentum back out into the cloud. And at this point I say, oh good, job done, you've got a protostar and somebody else's problem now. But this, very, very broadly, is our understanding of how low mass stars form. High mass star formation, a bit more of a mess, but we start from the same place. We start from a molecular cloud. And we still find filamentary structure. We find filamentary structure essentially in every cloud, regardless of how low or high mass it is. But it seems like the filamentary structure does something different in high mass clouds. Whereas in the low mass case, we see fragmentation, each filament fragmenting to form sort of beads along a string. In at least some high mass clouds, the filaments essentially seem to serve as accretion streamers, just sort of pouring material down their length into a central, down the bottom of a gravitational potential well. And in the centre of these filaments, at sort of the bottom of the gravitational potential well, you have a hub in which the massive stars form. This is an example of a hub filament system. This is the Monoceros R2 star-forming region, which is only about 800 parsecs away, so relatively nearby as these things go. And you can see, geometrically, it looks very different from Taurus. Rather than having this complicated diffuse network of filaments, it's got a centre and everything seems to be involved with what's going on in that centre. What's going on in that centre, though, a bit more of a mystery. There are theories. We don't really know, because a high mass star formation is complicated by, firstly, by the time you get to around 8 solar masses, you ought to have hit an Eddington luminosity limit where it's impossible to accrete more material because of the photon pressure from what you've already formed. So how do you acquire several hundred solar masses worth of gas, perhaps, in order to hold it against collapse long enough to create a single massive star? Hard to do. So whether or not there's a high mass analogue of the low mass prestellar core remains very much up for debate. Quite often people say they found one, and then you look at it with an interferometer and it turns out to have an embedded protostar. An alternative theory is that inside one of these hubs you see lots of little low mass protostellar cores, and they sort of fight amongst themselves for mass, that competitively accrete from their surroundings, and some of these little seeds grow up to be massive stars. What goes on in these hubs is really still up for debate, and whether it's the same everywhere is also not well known. But what we do find is that consistently massive stars don't form in isolation. Wherever you see a massive star, you're going to have formed a large number of low mass stars as well. And the question is then, is that just simply statistics? It's so improbable that you form any high mass star anywhere that just the laws of probability say there'll be some low mass stars as well? Or is it the case that you must have low mass stars in order to form high mass stars? The latter of those is the competitive accretion argument, where you must form a large population of stars and one of them becomes massive, one of them wins. The other one still allows for sort of high mass prestellar cores, but there's a lot still that we don't know about here. But the other thing about high mass star formation is it affects its environment in a very big way. So you have the outflows from the forming stars, as you do in the low mass case. You also have photon feedback, so you form H2 regions around these massive stars, ionize their surroundings, immediately make it more difficult to form more stars in the immediate vicinity, while possibly triggering star formation in the surroundings as you sort of send a shockwave out into the cloud. And then within a few mega years, if they're massive enough, they're going to explode. And if they're still embedded in their parent cloud when that happens, it's going to have consequences for that cloud. So high mass star formation does suppress star formation, it seems, in its immediate surroundings, while possibly being the cause of further star formation further away. So yes, that's an extremely brief tour through the star formation process. But I've not, in fact, mentioned the magnetic fields at any point in all of that. So if in most seminars, the obvious question to ask at the end is, but what about the magnetic fields? You can ask me, because I probably still won't have given us a very coherent answer. But the Milky Way has an absolutely beautiful magnetic field. All spiral galaxies seem to. Magnetic field that runs along the arms of the galaxy. You can't see it very clearly in this image because we're in the galaxy, so naturally it's hard to see what's going on. But you can see the magnetic field in the plane. You can see in the nearby molecular clouds Ophiuchus there, Corona Australis, Orion down there, and think some of the complexity of the magnetic field in these clouds. So we know that the magnetic fields are there, and we know that they're spreading the interstellar medium on all size scales. So the question is, what dynamical role do they play? What do they change by their presence, if anything? And the way that we investigate this is using dust emission. Well, the way I personally investigate this is using dust emission polarimetry. There are other methods out there, but this one is very widely used. So the molecular clouds, mostly composed of molecular hydrogen, which usefully is completely invisible to us. If it's below a temperature of about 500 Kelvin, and we're about 10, 20 degrees above absolute zero in these clouds. So we have to look to alternative tracers if we want to know what the gas is doing. Dust is a great material, great thing for doing this because it emits broadly as a black body. So if you observe the sub-millimetre continuums between sort of tenth of a millimetre and a millimetre, you get broad continuum emission that's just tracing the emission from the dust grains. And we hope and trust that those dust grains are well mixed in with the gas and there's a relatively constant ratio of gas to dust. And then we say that we can use dust as a proxy for gas in molecular clouds. And that's great, but also we can use the dust to trace the magnetic fields. So dust grains, they're absolutely not nice little spheroids like this, but we can sort of pretend that they are for our purposes, because what they're definitely not is spheres. They've definitely got a major axis and they've got a minor axis. And if there were no magnetic field in the cloud, we wouldn't expect there to be any preferred orientation for any given dust grain. They'd all just be completely randomized. But these dust grains, we call them dust, but of course they're not dust as we'd recognize it on Earth. They're composed of, carbonaceous compounds, silicates, ferrous materials, so more like sand and soot and iron filings. But helpfully, some of those species are paramagnetic. And what we find is that if there is a magnetic field running through the cloud, dust grains very consistently align with their minor axis parallel to the magnetic field direction. That this happens has been known about since the late 1940s, but it's only really in the last 10 years or so that it's been nailed down why this happens. It's not particularly intuitive. What seems to happen is that photons collide with the dust grains and impart angular momentum to them, and they start spinning. And because they're paramagnetic, they end up with their momentum vector aligned with the magnetic field direction, and so process around the magnetic field. But for our purposes, that means that if we can measure they have a major axis along which more is going to be emitted, so they have a preferred direction for their polarization. The light from the dust grains is preferentially polarized perpendicular to the magnetic field, which is great because then we observe it. We stick a half wave plate between us and our detector. The JCMT uses a half wave plate. More modern cameras are starting to use kids technology that can do this intrinsically, but we have the half wave plate and all of the problems it brings for your optics. That is the half wave plate. It's just an insert in front of the Scuba 2 camera. And then with all of that, you can get a polarization angle out of your measurements, and you get a polarization fraction. I am not going to talk about polarization fraction at all because it's a horrible quantity, and It would be an entirely different talk about dust physics if I did, but there's a lot of useful information in the polarization fraction that I am absolutely not going to talk about now, but do ask me if you want to know. But for our purposes, you take your polarization angle, you rotate it by 90 degrees, and you've got a tracer of the plane of sky magnetic field direction. So great, that's what we've got. The next question is, I've just said repeatedly, over and over again, these are molecular clouds. They're made of molecular gas, molecular hydrogen, not known for being ionized. So why should neutral material, which these clouds overwhelmingly are, why should they care in the slightest what the magnetic field is doing? And the answer to that is because of flux freezing. So essentially, even though ionization fractions in molecular clouds are very, very low, they're not quite zero, sort of could be as low as 1 part into the 10 to the 7 or even more than that. But there's just enough ions that the mean free path for collisions between ions and neutral particles is short enough that they're coupled as fluids. So the ions move with the magnetic field, the ions and the neutrals move together. So until you get sort of the densities of protostellar disks, the centers of prestellar cores, you don't need to worry about this at all. Essentially, the material behaves as if it were an ionized medium in terms of its connection to the magnetic field. So that's why we can still talk about the effect that a magnetic field has on a molecular cloud, even while I repeatedly tell you that molecular clouds are not ionized. It nonetheless works. So what do we expect magnetic fields to actually do to gas? I mean, essentially provide resistance against gravitational collapse. Magnetic field lines don't want to be pushed together, so it provides an extra pressure term in the cloud, which should make it harder for gravity to collapse one of these clouds and form stars. However, while the magnetic field provides an extra pressure term, it doesn't provide it equally in every direction, because it's very, very easy to move along a magnetic field line if you're a charged particle, but almost impossible to move across it. It's almost like the difference between trying to move beads up and down a guitar string and then move them from one string to the next. I mean, maybe that's an exaggeration, but... so essentially, material can collapse along a magnetic field as much as it likes, but if you want it to then collapse inwards, you've got a much more difficult job on your hands. So magnetic fields can essentially, as well as providing an extra pressure term, also provide a sort of symmetry breaking term, providing a preferred direction for the gas to move in. So a characteristic of this is sort of held up as the ideal, the thing that you would see that's a definite and absolute characteristic sign of a strong magnetic field, is this hourglass morphology that we call, as it's called, which we would expect to see in dense cores if they were evolving in a strongly magnetized state. And they have been seen, these hourglasses. This one is observed by Girard et al. Has he actually ever visited?
No,
never visited. Okay, well, try and get him over here. So this is an example of a low-mass protostar in Perseus, which shows this very nice hourglass shape. And I could maybe find one or two more examples of this. But it's not sort of slam dunk, we see this, therefore clearly star formation proceeds in a magnetized fashion. I could probably find you plenty more examples, of course, that don't have this nice straightforward morphology. But it does seem like there is at least potentially a strongly magnetized channel for star formation. Maybe not all stars form in this way, but the pathway does seem to be there. So how do we actually measure this? Sorry, a lot of equations on this slide. The key point I'm trying to make is what we're usually doing is comparing magnetic fields to the other energy terms. So compare them to gravity, we measure the mass to flux ratio. Compare them to non-thermal motions, then we want the alpha Mach number, which is an analogue to the sonic Mach number. And if we're just interested in how they're compared to thermal pressure, we want plasma beta. The reason why I've put this horrible mess of equations on here is for all of these, this one needs a magnetic field strength. That one, I haven't actually written it all out, which doesn't help. Oh yes, I have. Needs magnetic field strength. This one needs magnetic field strength squared. In all of these, we need a magnetic field strength if we want to quantify any of these. which is all well and good, but what dust polarization observations give us is the magnetic field direction. So how do we go from understanding what the magnetic field is doing in the plane of the sky to actually quantifying how important it is? To do that, we need the Davis-Chandrasekhar-Fermi method. So there's two things you need to know about the DCF method. The first one is it's definitive proof that no matter what you want to do in astrophysics, Chandrasekhar got there first and he did it better than you. And secondly, it's a good way to start a fight in an empty room. This is a horrible method. Nobody should be using this. But no one has had any better ideas since 1950s, so we keep using it and we keep striving to make it slightly less bad. What we're doing is we're measuring how much the magnetic field lines wobble. So we're saying we think there should be an ordered underlying mean magnetic field going through this cloud. So any dispersion that we see in the magnetic field vectors, other than instrumental uncertainty, means that the magnetic field is being moved around as the gas moves, and it's turbulent motions, essentially, that are distorting the magnetic field. So we measure how much the magnetic field lines wobble around, we measure the angle dispersion, and that gives us a measure of the alpha Mach number. We then pick a gas tracer that we think is tracing the same material as the dust, measure its line width and say, great, got a line width, multiply it by that and get an alpha velocity. We then take a look at our two-dimensional observed in the plane of the sky cloud, try and work out its 3D geometry and infer a number density, multiply it by that. Then we pick a number between 0 and 1 as a correction factor, put it all together and say, look, we measured the plane of sky magnetic field strength. Now, the astonishing thing is not that this doesn't give us the right answer. The astonishing thing is it works far better than it's got any right to. So we compare these observations to Zeeman measurements. So measurement of the Zeeman effect is the gold standard in that it gives you an actual magnetic field strength that you can actually believe, but it's also absolutely nightmarishly difficult to observe. This may not be true in a couple of years. When the square kilometre array comes online, we may be making Zeeman observations routinely, but for the time being, we've got a few of them and we use them sort of to calibrate. A lot of people have been working on this over the last few years, but it seems that DCF does actually map magnetic field strengths. It overestimates them, which is probably not surprising because every bias in the method tends towards overestimation, but not by orders of magnitude. The DCF method does seem to give you a broadly reasonable magnetic field strength, which is great. It's important to remember, though, that overestimating your magnetic field strength by a factor of 5 means you've overestimated your magnetic energy by a factor of 25. So we do need to be aware when we're using this method that there are a lot of biases involved. But it's a lot better than nothing. Another alternative is to look at how the magnetic field structure behaves and how the magnetic field structure relates to the density structure. So these are two simulations. This is work by Juan Soler. The one on the left has a weak magnetic field and the one on the right has a strong magnetic field. And what gets found, not just in this simulation, in many simulations, is that very consistently, if you've got a strong initial magnetic field, density structure forms perpendicular to that magnetic field. And if you've got a weak initial magnetic field, then the density structure runs parallel to the magnetic field. So essentially, in the weak field case, the magnetic field just gets dragged around as the gas moves. Wherever the gas goes, the field goes too. It's frozen in, but it can't control the dynamics. Conversely, in the strong field case, material falls in along magnetic field lines and essentially forms pancake structures perpendicular to the magnetic field. So that's a nice, relatively straightforward prediction for different magnetic field morphologies that you would expect in strong and weak field cases. And okay, so we kept the strong field one on the right, and on the left here we've got Planck observations of the torus molecular cloud. And they don't look wildly different. So it does seem that fairly consistently in the interstellar medium, gas at sort of molecular cloud scales, we look a lot more like the strong field predictions than we do the weak field ones. Density structure is preferentially organised perpendicular to the large-scale magnetic field direction. So it does seem like, at least on some scales in this process, the magnetic field is dynamically important in how structure is formed. This is usually, but when you go inside the clouds, it gets a bit more complicated. So these are some cartoons actually that my PhD student Zach made, and I immediately borrowed for all talks ever. So on the right here, we've got the high mass star formation case, and on the left and right, left. That's left. That's right. On the left here, we've got high mass star formation case, in which we expect material to be flowing down the filaments onto a central hub. And on the right, we've got the low mass case, where we simply expect fragmentation into individual dense cores. So the prediction would be that for the high mass case, we have magnetic fields that run parallel to the filaments. The gas is flowing inwards, and the magnetic field will run parallel to the filaments, because it's just, at this point, everything is gravitationally dominated, and the magnetic field is going in with the gas. In the low mass case, however, we would expect the magnetic field to stay perpendicular to the filaments as they fragment. So we have different predictions for what we expect to see in the high mass and the low mass cases. And this is quantified using a tool called the histogram of relative orientations, which essentially, the most important things are the x-axis here is column density, so we're going from low density to high density, and the y-axis, if you're up the top of the plot, then the magnetic field is parallel to the density structure, and if you're in the bottom half, you're perpendicular. So in the low density interstellar medium, we see this transition from parallel at low densities to perpendicular at high densities, which, broadly speaking, indicates that at some point or other, the magnetic field starts out as being dynamically important, and at some not very well specified column density, it changes and gravity wins. And that's fair enough. Eventually gravity has to win, or we wouldn't be here having this conversation. So this behaviour is pretty consistently seen. And it's seen in both simulations and it's seen in observations, but naturally that doesn't mean that we actually understand what's going on. So this is a plot that Ava Entomusi put together for our Protostars and Planets article. And she sort of scoured all of the simulations and plotted the density at which they predict that this transition from preferentially parallel to the field to preferentially perpendicular, which is probably some sort of indicator of whether or not the field is dynamically important compared to gravity, see where it occurs. And the answer is the different simulations disagree with each other by 4 or 5 orders of magnitude on the density at which this happens. So although we can all pretty much agree that it must happen, deciding where in a cloud it happens, at what density, when does the magnetic field stop mattering for the gas dynamics, or at least stop controlling the structure formation, we have no idea, so we need much better observational constraints, which is our answer to everything, unless you're an observer, in which case we say we need better simulations for us to interpret this with. So one of the big questions that we wanted to answer with the Bistro survey was, can we pin down a density? Can we look at molecular clouds with our relatively high resolution observations and see where this transition occurs? And the answer to that is, by the time we can see it in our JCMT observations, the transition already has occurred. So I'm just going to show you a few examples of what magnetic fields look like in star-forming filaments. This is the Perseus NGC1333 cloud, which is around 300 parsecs away, low-mass star-forming region. And up here, these are the Planck data. So we can see the magnetic field essentially running perpendicular to the filaments, as we expected. But when you come down into here, you probably can't see it very well on this screen, but I assure you, it looks like they're all over the place. But this, it turns out, started out wondering, what's going on? There's a clear prediction for low mass star formation, and this is not what's happening. We're seeing some parallel, some perpendicular, some in between. But of course, what we're seeing here is the magnetic field in the plane of the sky. So we're only seeing the projection of the field in these filaments. So this is work by Yasuo Doi. And he did a statistical analysis, and this is completely consistent with the magnetic field being perpendicular to the density structure in 3 dimensions. The column density here is of order 10 to the 23 particles per square centimetre, so at least in this environment, at that column density, we're past the transition point, and as far as we can tell, everything is gravitationally dominating and fragmenting. This is Serpent's main. This is work by Wu Jing Quan from a couple of years ago. Again, we've got histogram relative orientations. Key point is everything is in the half that suggests it's gravitationally dominated. There's a lot of complexity there. He has a model of sort of fields getting pinched in the centre of dense cores, but broadly speaking, again, column densities are quite high and gravity is 1. So this is NGC 6334. This is a higher mass star-forming region. This is about 1.3 kiloparsecs away, and it's a dense star-forming ridge. You can see there this filament. And on average, again, 10 to the 22 to 20 to the 24 centimetres per particles per cubic centimetre, and very consistently the magnetic field is running perpendicular to the dense ridge. So this is perhaps less insightful than we'd hoped, but it does at least give us an upper limit. By the time you can observe it with the JCMT, it's already past the point of this transition, which is useful information to have. But something that I think is really interesting in NGC 6334 is that I've been talking about high mass star formation and low mass star formation if they were completely separate modes, and the cloud has to essentially picks either low mass or high mass star formation, does one or the other, but that's not the case at all. You can easily see both modes of star formation happening in the same cloud, and they're probably nowhere as distinct as I've been saying they are. So here, for example, if you pick one of these subfilaments, this one here, for example, when we're away from the central ridge, we're much further out of the gravitational potential well, the magnetic field is perpendicular to the filament, which is our prediction for a low density, a filament forming low mass stars. But then you follow the same filament in, and the magnetic field turns to be parallel to the filament and perpendicular to the main dense ridge. So while it looks like, on the whole, this is tracing flow of material down the filament onto a hub, out in the periphery, we have a filament that's fragmenting into dense cores, as we would expect in the low mass star formation case. So we have both high and low mass star formation happening, not only in the same cloud, but in the same filament within a cloud, which I think is really interesting. Something that I'm hoping we can follow up further. I have no idea what time it is, by the way. If I'm massively overrunning, someone do tell me, or I'll just carry on, So this brings me on to something that we've done with the Bistro data that we weren't expecting to. So this is not something that we went looking for, but I think it's probably one of the most important things that we've got coming out of the survey, and that's the relationship between magnetic fields and feedback. So it's increasingly coming out of simulations, the idea that if we want to set star formation efficiency, we don't just have to worry about the effect of stellar feedback sort of quenching star formation in the cloud, and we don't just have to worry about things like non-thermal motions and magnetic fields providing pressure to slow down the formation of stars. The connections between feedback and magnetic fields may play a very important role in essentially making feedback non-local. Rather than it just affecting its own immediate environment, you take your outflow feedback, couple it to the magnetic field, and suddenly it can act over a much larger area of the cloud. This is predicted by simulations. The one on the left here is without a magnetic field, and the star formation is clustered and the outflows are relatively smaller. On the right-hand side, with the magnetic field, the star formation is more dispersed, and also outflows can propagate over significantly larger distances. So do we see any sign of this in our observations? Maybe, yes. It seems wherever we look in the immediate vicinity of protostars, we see magnetic fields that have been distorted by the outflow. This might just mean we're preferentially tracing dust in the cavity walls of the walls of the cavity that the outflow opens up. But even so, I think it tells us something important about the effect that essentially turning on a large amount of feedback does to the magnetic field in your surroundings. So this one here, published by Arang Yeo, this is Orion, a massive protostar in Orion B, and it's probably easier once it's been drawn on to see it, but the magnetic field shape does correlate very well with the opening of the outflow. This is actually not Bistro data. This is some of my own data on a very, very boring Bok globule called CB54. It's not exciting. It's forming 3 low mass stars. Nothing. It's sitting in complete isolation. The least interesting star formation region you've ever seen, essentially. And yet, even here, these tiny little low mass protostars seem to have completely reshaped the magnetic field in the globule. I've helpfully not drawn on the Planck magnetic field, but it goes through like this, and where we see the outflow, we see a very, very distorted magnetic field, even for a weak outflow from a low-mass protostar. And I think this is one of the nicest, clearest examples. This is work that my postdoc Yannick did last year, when he was still a PhD student. So this is the L43 protostar. It's a low-mass protostar off Fucus, so only about 140 parsecs away, so we can really see the detail. And this outflow has just taken a chunk out of the cloud. There's some really beautiful amateur astronomy images of this cloud, in fact, where you can just see a hole in the cloud, that, as we can see here, the cavity wall, the outflow has just opened up. I can see the magnetic field here running along the outflow cavity wall, and we can see the same thing over here. Completely different from the field in the parts of the region that aren't affected. So we really do see very consistently magnetic fields being reshaped by protostellar outflows. Essentially, whether we're looking at a high mass protostar or a low mass protostar, this is what we seem to see. This has been quantified. This is work using Bistro data done by Xiwei Yan a couple of years ago. So what they did was compare the direction of the outflows and the directions of filaments for every class 0 protostar in the Bistro sample. And what they found is that it's consistent, helpfully, it's consistent both with being completely random and with having a preferential inclination of 50 degrees in 3-dimensional space. So the most probable model was outflows and magnetic fields misaligned by 50 degrees in 3-dimensional space, which is a bit odd. No obvious reason it should be like that, unless they are preferentially tracing the outflow cavity walls. So that was our going model, but also should be noted we couldn't rule out it just being completely random. So this is on sort of 0.1 parsec scales. There are ALMA studies doing similar things on smaller scales that see probably behaviour that's closer to random. So there's a lot here that we don't understand really about the relationship between magnetic fields and outflows and whether, but it seems unlikely that magnetic fields can sort of direct outflows statistically, but it does seem like there is some sort of coupling between them and some sort of preferential alignment between magnetic fields and outflows, which I'm choosing to interpret as probably traces the cavity walls, but I'm sure somebody else could give you a different explanation for the data. I do just want to point out, though, this isn't exclusive to protostars. So this is a paper that just resubmitted last week, which is a radical departure for me because this is completely the other end of the life cycle of a star. These are magnetic fields in preplanetary nebulae, sometimes more often called protoplanetary nebulae, but the referee insisted we had to call them preplanetary nebulae so we wouldn't confuse people, but I think it's even more confusing. So, worst named things in astronomy, but protoplanetary nebulae. The end of the star formation process as the star transitions from being an AGB star to being a planetary nebula. So it's hard to tell from these observations because they're barely resolved using the JCMT, but as far as we can tell, again, this one is consistent with the opening angle of the bullets that are being ejected from the central star, and this one seems to be being reshaped as the structures here expand. So again, where we see feedback acting on a magnetic field, it seems like we see the magnetic field being reshaped, even in a completely different environment. So that's outflow feedback. The other type of feedback that I'm going to talk about briefly is stellar feedback. So again, we expect magnetic fields to have a role to play, particularly in the evolution of H2 regions. So on the left here, we've got, again, a simulation. On the left, we've got an H2 region evolving in the absence of a magnetic field. And on the right, we've got an H2 region evolving with a stronger magnetic field. And whereas and essentially this is back to the magnetic field providing pressure and it providing an extra pressure term, or rather in this case a tension term, making it harder for the H2 region to expand, because as it's trying to expand, the magnetic field is trying to essentially pull back in. So on the left, we've got the H2 region breaking out of the cloud, and on the right, we've got the H2 region remaining confined because the magnetic field is preventing its expansion. So what do we see when we look at star-forming regions? We see pretty consistently magnetic fields apparently reordered to run around the edges of H2 regions or along the edges of PDRs. So this here is back to NGC 6334. This is, again, work by Doris Artzemanian, picking out an H2 region where we see no signal in the centre, and around the edge we see essentially concentric magnetic fields. This is the Orion bar, which is an edge-on photodissociation region bordering the trapezium cluster. And again, the magnetic field seems to be running parallel to the length of the bar, so it's clearly been rearranged. And the question then is it dynamically important if it's been rearranged? And that does seem to vary a bit depending on the region. The left here, we've got the Horsehead Nebula, where it seems like essentially the magnetic field has just been completely reorganised in the PDR up here, but that does seem to be sheltering a dense core that's continuing to behave as if the PDR weren't there. On the right, we've got the famous pillars of creation. And in this one, we did an energetics analysis and found that while the magnetic field can play absolutely no role in preventing the erosion of the pillars by the expanding H2 region, it might be sufficiently strong to essentially, the magnetic pressure within the pillars pushing outwards is enough to balance the thermal pressure of the surrounding H2 region that's trying to disconnect the pillar and turn it into a cometary globule. So the magnetic field might be playing some role in stabilising the pillars. It's essentially just been distorted to the point that you've reached some sort of balance. And then we get regions like this. So this is work by my PhD student, Zach, that just went onto arXiv last week. And I think this is really quite a fun region. So this is G34.26 plus 015, catchy name. We didn't think of a nickname for it. We probably should have done. So this is an incredibly bright star-forming region, to the point that this central hub here is a secondary calibrator for for at least some telescopes. But the surroundings hadn't really been studied very far. And I think it's a beautiful case study in what feedback does to your star-forming region. Because there's a couple of deeply embedded H2 regions in the centre here that we can't resolve, so we don't really take any interest in. And then this massive one here, H2 region D, you can see here it's in Spitzer C and VLA C-band, I think. So you've got a big open H2 region. And what we see is that on the left side here, the northwest side of the globule, we just see a radial field structure. Everything seems to be falling in towards the centre, exactly as all of the models of high mass star formation, hub filament systems, so on and so forth predict. On the right, we see a magnetic field that's just been completely reshaped by the H2 region. So it's running around the edges of the H2 region rather than following the density structure into the centre of the hub. So it's sort of a before and after, you know. If we just saw the southeastern half of this globule and were asked to infer the initial conditions of the magnetic field for when star formation turned on, we'd have no information to go on. As soon as you turn on feedback in a big way, it seems that the magnetic field changes irrevocably. So if we want to understand the pre-star formation conditions of the magnetic field, we have to look at something before it's formed stars. Afterwards, we're not going to get information that we can use, at least for this purpose. It does tell us something very interesting about how H2 regions evolve, though. And this is just a cartoon that Zach made to try and show what he thought was going on. So in the last couple of minutes of my talk, I'm going to jump wildly, while still talking about feedback, to other galaxies. Star formation, I've been considering it as a local process, but of course it affects everything. It affects how galaxies evolve. It affects the entire baryon cycle, and to a certain extent, and magnetic fields in galaxies connect to magnetic fields in the intergalactic medium. So, although I've been focusing right down on the smallest scales, there's turtles all the way up as well as down. So the data, I'm just going to briefly show you some observations of nearby galaxies made as part of the JCMT Nearby Galaxies Legacy Survey. This is data that was taken in sort of the late 20, up until about 2010. And the HARP data, the spectral line data, was published about 15 years ago. The JCMT data, we managed to publish the first bit of it last year. It's just because the data reduction process has moved on and we've been able to start to recover structure. So I'm mostly showing you this just to demonstrate that it is possible to observe nearby galaxies with Scuba 2, because if you've used Scuba 2, I would understand why if you said, no, you can't, don't be silly. But it can be done. It's an absolute nightmare, but you can do this. So of course, my thought was, fine, we can observe, we can detect them with Scuba 2. Can we point the polarimeter at it? Can we see the magnetic field in any of these? And the answer is only in the really, really staggeringly bright ones. So we've only managed to get detections so far for 2 starburst galaxies, but I do think that they both show us something very interesting. So just as a reminder, what we expect to see in a spiral galaxy, if nothing else is going on, is a magnetic field that's running along the spiral arms of the galaxy. The arguments for exactly where this field comes from is still open. There's a good review article by Brandenburg and Entamusu from last year if you're interested, but suffice it to say, we do see magnetic fields running along spiral arms, and that's what we expect to see if nothing else is happening. M82, which is the first one we had a go at, it's the nearest starburst galaxy to the Milky Way, and it's got a central starburst. It's got a really, really dramatic starburst happening in its central region, triggered by an interaction with its neighbour. And it's got a very famous superwind, so the sheer number of supernovae in this central starburst is driving an enormous wind which extends more than 10 kiloparsecs above and below the plane of the galaxy, absolutely enormous outflow structure. So where we saw outflow structures in nearby molecular clouds, completely different size scale, but they distorted the magnetic field. So what did we see in M82? Something very similar. So around the edges of the galaxy, we see a magnetic field that, well, to be honest, at this signal-to-noise ratio, it's very difficult to say for certain whether it's toroidal around the galaxy or running along the spiral arms. But we've got no reason to think it's not running along the spiral arms. That's what all of the models predict, and the spiral arms are there, so that's what we think it's doing. But in the centre, the magnetic field is essentially aligned with the outflow. So we've got a poloidal magnetic field in the central starburst and a spiral arm aligned field in the disk. So turns out this is overshot. This is precisely what Terry Jones predicted 20 years ago. So there we were thinking we'd found something new and thrilling, and it turns out that Terry predicted it ages ago, but it's nice to see the model's working. And what we see is, once again, you turn on feedback and you move the gas and the magnetic field goes with it. Just another example here, just showing a little bit more of the context, showing the direction of this superwind, and the magnetic field really does seem to align with it. What we found that's really interesting is that when you deproject this and work out how far above and below the plane we see this poloidal behaviour, we see it break from poloidal to toroidal at a distance of around about 350 parsecs above and below the plane of the galaxy, which is exactly where the models predict that the superwind breaks out from the dense gas. So it all holds together very nicely. And if you observe this at shorter wavelengths in hotter dust with the Sophia telescope, which sadly no longer exists, they see this poloidal structure continuing to much, much higher galactic latitudes. So it seems like if you trace hot dust, then you see much more of the outflow structure. And when you see what we're tracing, the cold dust that's confined to the plane of the galaxy. So it all holds together very nicely. So having managed it with one galaxy, we thought we'd test our luck and have a go at a slightly fainter starburst galaxy, NGC 253. And this is work that I haven't quite finished yet, but Walter is glaring at me from Ireland, so at some point I will. So this is another nearby highly inclined starburst galaxy, but with the spiral arms much more clear now. And very broadly speaking, we see the magnetic field running along the spiral arms and the bar as we predict. But there are exceptions, and I think it's the exceptions that are really interesting. So we see magnetic field in the central starburst that seems to be somewhat connected to the outflow, which again isn't too surprising. This is what we saw in a much more dramatic, admittedly, starburst in M82. So again, large central outflow, large amounts of feedback can train the gas, and the magnetic field goes to, all holds together. But what I think is really interesting is we don't just see this in the central starburst. We see suggestions that in the giant molecular clouds and the spiral arms, the field of the entire cloud might be reorganized by star formation feedback. Not starburst, not the kind of starburst that's happening at the central nucleus, just regular star formation on giant molecular cloud scales. So I've just picked out two examples here. This cloud 6, where the magnetic field, I mean, it's not very clear what it's doing, but it's not running along the spiral arms. It's considering how highly inclined this is, these magnetic fields in this region could be directed out of the plane entirely. Hard to tell. But it's certainly been massively reorganized from the galactic dynamo field. And this one here maybe looks less interesting because we haven't got a detection, but I think that's what makes it interesting. This is the second brightest object that we have in the image, and we don't detect any polarization, which suggests that the small scale field is so complicated, it's been so disorganized by the star formation that we can no longer detect it. It averages away to nothing in our observations. So, and both of these are active sites of massive star formation. So really, what we're seeing on every size scale, from individual low mass protostars through entire molecular clouds to starburst regions and galaxies, is that there is a complicated relationship between outflows and magnetic fields, and I'm very excited over the next couple of years, while, to work out exactly what that relationship is and how we can use it to really understand how feedback changes star formation. So thank you very much.
Thank you so much. Really interesting and nice talk. Okay. Have questions, comments?
Camila is working in some nearby galaxies.
Yes, galaxies.
Several galaxies. So I was wondering if some of your galaxies can match their galaxies.
Maybe I mean, our observations are radio observations. We don't work with dust polarization, but I don't know. Yeah, maybe they are edge-on galaxies. We don't see the spiral arms, but some of them are not quite edge-on, so maybe we can match one of them. Yeah, they are pretty nearby galaxies, so maybe.
It would be really interesting to see, because dust polarization in other galaxies is just an absolute nightmare to do, and because they're both faint and extended, so and Sophia is closed, and the JCMT can only we've got the 2 or 3 that you can do now. So if the synchrotron data are out there, then sure there's something really interesting we could do to investigate
When
it.
do you plan to submit the paper?
As soon as I can get it finished. I mean,
This year or next year?
I'd like to say this year, late this year or early next year is my plan. And Walter, my old postdoc boss, is just going to keep shouting at me from across the Irish Sea until I actually do it. So it will get done.
Okay, I have another question. Thank you very much for your talk. You were saying that the structure of the magnetic fields in galaxies, they have like outside, the geometry is toroidal, and then in the inner part it becomes colloidal. And what is the explanation or the mechanism behind that?
So that seems to only be the case in these starburst galaxies. So what we expect, forward one. What we expect in sort of a regular spiral galaxy where nothing exciting is happening is to see the magnetic field running along the spiral arms all the way into the centre. So it seems like essentially the rotation of the galaxy creates a dynamo effect that results in this spiral field. What we think is happening in MAT2 is that the sheer number of supernovae in the central starburst, that's creating this massive sort of outflow chimney of just gas flowing straight out of the galaxy and into the circumgalactic medium. And we think that the magnetic field is essentially moving with that outflowing gas. So it's the supernova feedback and the large-scale outflow that's just dragged the magnetic field into a new configuration. But we only think that's happening because of the starburst. In a regular galaxy, we think the field would just go straight in.
Okay, thanks. And another question is not clear for me. When you were talking about stars and the outflows in protostars, what is the relation between these outflows and the magnetic fields? How are these outflows driven?
So the outflows are driven by the central protostar. So you've got an accretion disk around the protostar, and material is being essentially either accreted onto the star or thrown out as an outflow. And it is probably a magnetically launched outflow from the disk. But the fields that I was looking at was in the surrounding cloud. And essentially, I don't think we quite understand yet the relationship between the two. But what we're seeing is the magnetic field in the surrounding cloud is frozen into the gas of the surrounding gas. And the gas is being reshaped as the outflow essentially punches a hole through the cloud. And it just gets shoved out the way. And what we're seeing is the magnetic field and the gas all moving as the outflow cavity opens, is my interpretation.
Okay. Thanks.
Thank you.
I have a question that's from my ignorance. When you put the slides without the equation and you mentioned three main effects that are involved, the straight up and magnetic field. There is, of these three, there is one that is more, its presence is more effective than the other ones, or there is a ranking of effects, or are all the three taken in the same level?
So we don't, it's not very clear. So eventually, the three were gravity, non-thermal motions, and thermal pressure. So I think probably of those, thermal pressure is the least significant in most environments, probably. Usually what we're looking at is the relationship between magnetic fields and turbulence. So essentially, which of those is more important in supporting a cloud against collapse. And to be honest, so that's quantified using the alpha and Mach number. And to be honest, very often it's indistinguishable from one when we use the DCF method. Very, very often we get alpha and Mach numbers very close to 1. And it's not entirely clear whether that's actually true or if that's a failure of the method. In a way, it's hard to understand how you'd get a number much different from 1, because how would you hold all of the energy in the magnetic field and then have very, very weak turbulence, or vice versa? So most things are probably not very far from equipartition, probably, I think. That being said, so the mass to flux ratio, the relationship between magnetic fields and gravity, that one really should, eventually gravity has to win, right? So at some point you have to get to a very, very high mass to flux ratio, just because eventually gravity has to win over all the other forces.
But I mean that I have observed polarization in the optical, but in pixels that also is The reason is synchrotron emission of the jet, and at the end, the first component of the jet is this particular are driven by the up-bend waves through along the magnetic field. So I guess because of that. But the way of the direction of the magnetic field is made by the up-bend waves. So it's the first, at least the first time.
No, here we're being quite imprecise with our definitions, I think. So we use alpha Mach number to essentially quantify the relative importance of magnetic fields in any non-thermal motion. So sometimes that means turbulence in the cloud, and sometimes it's sort of ordered inflow. We're very inconsistent with how we use it.
Sorry, another question about these galaxies, the magnetic field in another galaxies. In any of the models and observation, you're taking into account the presence of black holes in the middle?
No, to be honest, our modelling isn't that sophisticated.
It's a nightmare, but also could be an explanation from some of the magnetic field.
It could be. To be honest, I don't know a huge amount about galactic dynamo theory, so they might include that in their models. But there are. These are very low resolution compared to the galactic centres, but actually
those are really nice observations.
But actually, last year, Enrique Lopez Rodriguez published an ALMA observation of sort of giant molecular clouds right in the centre of NGC 253, and sort of in the really, really high resolution in the central starburst. I don't think they actually saw anything related to the central black hole, but if we could get observations of more of these galactic centres with ALMA, we might see something interesting. Actually, I didn't show it, but we've got Bister observations of the central molecular zone of the Milky Way, and we're seeing a sort of magnetic field running along the sort of figure of eight gas structure there.
Okay.
So
nice.
Yannick's working on that. I'm hoping that we'll get that submitted before Christmas. So hopefully soon that'll be out there.
Nice. Anybody else?
Yes, I have a very basic question. I don't know if I understood correctly. Why is that the dust grains have that elongated shape?
To be honest, I'm not really a dust physicist, so I don't really know. I just take it on trust that they do. So they're sort of, as far as I understand, anyone feel free to jump in if I'm talking rubbish, they're sort of crystalline structures. So there's things like olivine and the same sort of material as we see in comets, pristine material in the solar system. So I think it's just, they're definitely not spheroids, but I think they just have irregular shapes, essentially. They're not nicely well constrained with a major axis and a minor axis. They're just, all of them irregular crystalline shapes, and they'll be just longer one way than another. But if anyone else knows more about it, then I just take it on trust.
They have irregular shapes. I mean, it's just that's it. It's not an issue. But they rotate around the minor axis because this is the minimum inertia or maximum inertia axis, and then they become perpendicular. On average, we are talking about maybe between 10 and 20% polarized emission. So not every single grain is aligned or is with this shape, right? But if you have a 20% population of elongated grains, then you get a 20% polarization intensity, something like that.
Thanks. I have a question from the chat. Sorry. the flocculent galaxy NGC 5055.
I mean, I'd like to. It's absolutely beautiful. So NGC 5055 is absolutely beautiful. I think it's probably too faint to do with the JCMT. I haven't actually checked though, so I'd love to. Is the short answer.
One more thing about the JCMT, the telescope JCMT, Argentina and Brazil, we are not official partners, but we are unofficial partners. And the deadline is soon.
Yeah, 9th of November. So if you want to submit anything to the JCMT.
Okay, Juliana, you know.
And you can also talk to Kate, and maybe she's interested in doing some research with you. So
Absolutely.
Okay. So, Juliana,
Yeah.
yes.
And if it's bright, if any galaxy is bright enough, I'd love to observe it.
Good. So let's finally thanks Kate.